Welcome to the course on audio signal processing for music applications. This week is the week of the short time Fourier transform, and in the previous programming class we talked about windows. We talked about how to get a window, how to display it, how to compute its spectrum, and how to visualize the kind of things that we talked about in the theory class related to windows. And now in this second programming lecture, I want to build the whole short time Fourier transform system and talk about the implementation we have in the SMS tools package. So we will basically be implementing the whole STFT equation shown here. So basically we'll be iterating over a sound X, and we will be computing at every frame. So the frame number is L. So we'll be computing frames of the sound. At each frame location, we will be multiplying the fragment of sound with the window W, and therefore at the end we'll have a sequence of spectra, a sequence of in this case complex spectra. And if we see it as a block diagram, so we start from the signal x of n, we multiply one fragment with our window, so we get a windowed signal. That's what we compute the FFT of, and then of course we compute the magnitude and phase representation of the spectrum, and then we can undo the whole process by calling the inverse FFT, therefore obtaining the windowed synthesized sound. And with what we call overlap add strategy, we will be adding together these fragments into a whole signal. And hopefully, if we have done the things correctly, especially if we have chosen the window at the hop size correctly, this output signal will be identical to the original. So let's look at the code of the STFT that we have in the SMS tools package. Okay, so this is the file called stft.py, and in it we have three functions. One, that is the STFT, that does the whole analysis and synthesis, and then we just have the analysis and synthesis separate, so sometimes it's useful. So we have the STFT anal function and the STFT synth function for the inverse part. But let's talk about the complete analysis synthesis. So let's talk about the STFT function. As input parameters, it has the X, our array with the complete sound. We need to know the sampling rate of that sound. Then we need to pass it the window we're going to be using, W, then the size of the FFT, capital N, and the hop size. How are we going to hop through the sound? And basically the core of the function is a loop, in this case a while loop, that keeps advancing through the sound by a pointer, this pin. Pin is a pointer that keeps advancing by H, by capital H, by the hop size. So pin gets advanced at every iteration by capital H until it reaches the N, which is the end of the sound. And within that, we basically choose the fragment of the sound that we want to analyze, and then we call the DFT anal function. So this is the function that we already discussed last week, which is the DFT model. It comes from the package DFT model. Okay, so we don't have to worry now here about the zero phase windowing, about the zero padding, etc. Everything is done within this DFT anal function, and it receives the fragment of the sound, the window, and the FFT size, and it returns the positive side of the magnitude and phase spectra. Okay, after that we can do the inverse DFT, also calling the DFT synth function, and therefore that will return a windowed fragment of the sound, and then we can put it all together, overlap and adding the sound and creating the overall output array. Okay, and apart from that, the rest are basically initializations and ways to better analyze the sound and to make sure that the pointer is can start at the very beginning of the sound and can end at the very end of the sound. So I'm not going to go into detail of that, but please feel free to go over that and understand this code. Okay, so now we have this function, so that returns a sound, and let's use it. Let's write some code to use this function. So this is a little script that I wrote to call the STFT anal, in which I first have to get all the packages required, including the actual STFT function. So this comes from the models directory. And then I can get a file, define the window, and then define the size of the window, the FFT size, and the hop size. And now we can read the file with waf read, get the window, and call the STFT function. And this will fill up two variables, mx and px, which will include the sequence of magnitude and phase spectra. Okay, so let's run it. Let's run test 3. Okay, that's quite quick. So it analyzes the sound and it obtains all these variables. So let's go through them. So maybe the first thing we can do is to listen to the sound. So we can just do the exclamation mark, play, and the name of the sound, which is this flute sound, and we can listen to that. Okay, so this is the sound of the flute. And now we can go through the different variables that we have computed. So for example, the first one is the sound that we read, the X array. So this is the whole sound, the array of the whole sound. So it's more than 80,000 samples. Okay, then of course we can plot the window that we computed, which is a humming window. And then we have the output array of magnitude and phases, but those are very big variables. They are very big matrices of values. So in fact, if we put mx dot shape, it will tell me the dimensions of the array, basically the number of frames and the number of samples in the spectrum that we have. So in fact, this tells me that we have 238 frames, and each frame has 512 samples. These 512 samples are the samples of the magnitude spectrum, of half of the magnitude spectrum. So now we can access individual frames of that. So if we put, for example, mx, and we access, for example, the frame number 50, and we plot the whole spectrum of that 50th frame, these are the values of the magnitude. And of course we can, if we call the function plot with that variable, we will plot the magnitude spectrum of that particular location. Okay, so this is the flute sound. We see the harmonics, and we see how the higher values are much softer, and it's quite noisy. Of course, we can also plot the phase spectrum of that same location. And this is the phase, the unwrapped phase, so we can see all these nice looking phase shape. Okay, of course, we want to visualize the whole spectrum. So in order to visualize the whole spectrum, the plotting command that can do that is what is, the function is called pcolor mesh. Pcolor mesh, it plots a matrix as a kind of a three-dimensional shape. So if we give it the the mx, it will basically plot all the frames, but maybe it plots it in a different way that we are accustomed to, because the vertical axis is the time. So in fact, we see time going from bottom to top, and the frequency is on the horizontal axis. In fact, a better way to plot these with color mesh is to transpose it first. So we can call the transpose function. So this will transpose the mx in a different way so that we can see it in a more meaningful way. So now we see time going from left to right and frequency going, or the frame, frequency going from bottom to top. Okay, so that's basically how we compute the magnitude, the phase spectrum using the STFT, and how we can plot it. And there is a function file that implements all that and makes plots in a nice way, and that's the STFT underscore function. And this is the one that is called from the graphical interface that we also use. And here it has one function called main, and it goes through the kinds of things we did, and it does both the analysis and synthesis. Okay, so the main has as input values all the input parameters, and then it reads the sound file, it gets the window, it performs analysis. This is exactly what we did now, but then it does the synthesis, and it outputs the synthesis file into a location with a given name, and then it writes it. Okay. By the way, here this file I just copied into the workspace, but I had to change the relative path of a number of these names. So, for example, I had to change the path of the software models, or I have to change the output file name, because in here it was using a particular directory to store the sound file. So here I just write it directly on this directory. Okay, so let's execute these. So I have it in this directory. So it's STFT function. So I can just run STFT function. Okay, and it plots well, the input sound, the magnitude, the derivative of the phase, and the output sound. And this has created a file which is called what is it called? Is called piano stft.wav. And of course from here again I can play it. So I can say play STFT piano stft.wav. Okay, and it's basically the same than the original sound. Of course, now from this file I can really change and make the things differently if I want. So feel free to change how the plots are shown. But this is a quite nice way to plot the things with the correct axes, with the correct labels, with the correct scaling, so that we can better visualize the analysis and synthesis using the STFT. And that's all I wanted to say. So basically we have gone through the short time Fourier transform, the implementation of the short time Fourier transform. So make sure that you understand the actual equation and what the signal processing considerations that are involved in that. And then of course we use a number of packages from Python together with the SMS tools that we have already developed and implement the DFT and the STFT. So we have been calling those functions. And that's all. So with this programming class, hopefully you have gotten an idea of how to implement the STFT and how can we use the functions of the SMS tools to actually adapt it to our own particular needs. So please feel free to play around with that and make sure that you understand the STFT also from this programming perspective. And that's all. Thank you very much.